The development of quantum fault tolerance and classical cryptographic compliance are converging. The harvest now, decrypt later threat model requires an immediate response. Because data captured today can be decrypted once quantum hardware matures, security protocols must be updated before that hardware exists. To address this, the NSA published the Commercial National Security Algorithm Suite 2.0. For defense suppliers, the software and firmware transition period began in 2025. Commercial post-quantum compliance is distinct from national security systems requirements. The parameter sets mandated for defense applications are more demanding than the standard commercial defaults. This chart compares quantum engineering speed against security compliance. Research reduced the physical qubit overhead for logical computation from 3,000 to 288, but the timeline for validating a classical cryptographic module remains fixed at 2 years. Physics is outpacing validation. Post-quantum cryptography has moved from a strategic roadmap to a current engineering requirement. Early quantum error correction relied on surface codes. These models used a two-dimensional grid where error checks only involved adjacent neighboring qubits. This architecture is limited by the Bravi-Poulin-ter-Hall bound. This mathematical constraint dictates that any code wired only between neighbors on a flat chip requires a high ratio of physical qubits to protect a single logical qubit. In a traditional surface code, protecting 12 logical qubits requires roughly 3,000 physical qubits. This overhead is a primary barrier to building a useful machine. A different approach uses quantum low-density parity check, or qLDPC codes, to bypass these 2D limitations. These are based on classical LDPC codes developed by Robert Gallagher in 1960. While originally too complex for 20th century hardware, they are adapted for modern quantum architecture. This comparison shows the difference in efficiency. On the left, the surface code spends 3,000 physical qubits for 12 logical ones. On the right, IBM's gross code provides that same protection using only 288 physical qubits. qLDPC codes use sparse checks, touching only a few qubits, to reduce overhead by a factor of 10. The trade-off is wiring. To achieve this efficiency, error checks must reach across the processor, replacing local links with long-range connections. Modern quantum hardware roadmaps are now incorporating custom long-range couplers to support this specific qLDPC wiring requirement. By removing 90% of the hardware overhead, qLDPC architecture shifts the potential date for a cryptographically relevant quantum computer much closer to the present. To defend against this, NIST and the NSA selected algorithms based on module running with errors, or MLWE. MLWE is an algebraic structure where the vector space is defined over a mathematical ring. This replaces simple integers with polynomials, creating a more complex mathematical problem for an attacker to solve. This is distinct from a classical modular lattice. The PQC standard specifically uses a module lattice, which is a structure designed to balance high security with computational efficiency. There is a specific requirement for defense applications. While the commercial standard is ML-Chem 768, national security systems are mandated to use the more secure ML-Chem 1024. These payload bars show the increased scale of the new standard. Upgrading from legacy RSA and elliptic curve cryptography to CNSA 2.0 demands significantly larger data footprints. ML-Chem 1024 requires a 1,568-byte public key. The mandatory MLDSA 878 algorithm requires a 4,627-byte signature. This parameter expansion exceeds the memory buffers and network bandwidth capacity of many legacy systems, creating performance issues long before a quantum attack is possible. Beyond the mathematics, defense contractors most navigate the regulatory requirements of national security systems. Procurement and implementation are governed by the DFARS and CMMC 2.0 frameworks, which dictate how security controls are applied to the supply chain. NIST Special Publications 800-171 and 172 require the use of FIPS-validated cryptographic modules. Unvalidated modules are not permitted in these environments. It is not enough for an engineer to implement the correct ML-Chem math. The specific implementation must be validated as a module through the government's formal process. The path to deployment is not direct. An open-source library cannot move directly into a national security system. It must first pass through the NIST Cryptographic Module Validation Program. Lead time for FIPS 143 validation is typically 12 to 24 months. This schedule must be aligned with the NIST IR 8547 timeline, which sets the dates for when legacy algorithms will be officially disallowed. Legacy algorithms are deprecated for new use starting in 2030. Subtracting the 2-year validation queue from that date reveals the actual deadline for engineering. Accounting for integration, testing, and approval cycles, the window for active development is between 24 and 30 months from today. Software availability is a prerequisite, but the FIPS 140-3 validation queue is the primary constraint on national quantum readiness. Defense primes and subcontractors must follow a structured, rigorous integration strategy to successfully meet these fast-approaching compliance deadlines. Maintaining CNSA 2.0 compliance requires a 6-point readiness plan. The first step is a cryptographic bill of materials, or CBOM, to inventory every cryptographic component within a program. The second mandate is a dedicated FIPS 140-3 validation strategy for each piece of architecture in that inventory. Third, all sub-tier suppliers must be audited. Prime contractors are responsible for ensuring that PQC requirements flow down through the entire supply chain. If a single subcontractor providing firmware or software libraries fails to migrate, it creates a vulnerability that can disqualify the entire program. During the transition, a hybrid approach is often used, as seen in this schematic for the X-Wing TLS handshake. Hybrid systems combine a classical algorithm with a post-quantum algorithm, providing protection even if one of the methods is later found to have a flaw. For national security systems, the PQC component in this hybrid configuration must specifically be MLChem 1024. Using the commercial default MLChem 768 in an NSS hybrid deployment will result in a failure of CNSA 2.0 audits. Protecting critical infrastructure is now a function of managing engineering deadlines and supply chain compliance.